Part 4 of 16.6, and here we start discussing surface area. And we are going to compute surface area of a parametric surface with a double integral. And so let's maybe take a little more time than we have already to kind of draw out what's really going on with these parametric functions of two variables. So we can draw out the u, v coordinate system here, and let's just say that in the uv coordinate system, the domain of R is some rectangle D, and that R then is a function which goes from the UV plane to the XYZ coordinate system. So R goes like this and comes over here and gives us some surface. So let's say it looks like this. Of course, again, my natural tendency is to draw something that's a function of X and Y, but not necessarily the case. So let's think about this. If S is smooth, in other words, it doesn't have sharp corners or anything like that, it's a differentiable function surface, then what we can do is we can start introducing partitions of, I guess I should really be partitioning here. So partition the U and V axes, and a partition of the U and V axes induces then these grid lines. So it becomes a sort of partition over here, right? And then what we think of is, okay, so maybe, you know, for a particular little subrectangle over here maps over to, say, a particular patch over here. I call these patches because they're not, here we would have a rectangle, everything is at a right angle, but here possibly there's some curvature. And so how are we going to approximate the surface area of a patch? Well, that's where it's important that S is smooth. So if S is smooth, or that we have a precise definition for this in terms of derivatives, but that's not important right now. If S is smooth, then the area of a patch is approximately the area of a certain parallelogram. So let's bring this patch out like this. So let's see the patch. Let's draw it slightly curved. And then at this point here, you've seen this, seen me walk through this before. These grid lines here, tangent vectors are given by, say R sub U at this point, and say U0, V0. And a tangent vector here R sub V at, say, U0, V0. But recall that the magnitude of the cross product of any two vectors gives the area of the parallelogram determined by those two vectors. And so these vectors here, then, these two tangent vectors determine a parallelogram whose area is approximately the area of the patch. So area of patch is approximately the magnitude of R sub U cross R sub V at that point. And that's the extent to which we're going to kind of walk through the, what would this, the Riemannian, chopping of things up. We're just going to go ahead and pass at this point to the area of the total surface S is the double integral over this rectangle D of the magnitude of the cross products of these vectors. So you really have to, if this doesn't ring a bell, this is chapter 12. One of the interpretations of the cross product was that the cross product of any two vectors, the magnitude of that cross product gives the area of the parallelogram determined by those two vectors. And that's an old fact from chapter 12 that we haven't talked about in a long time. So if that's vaguely familiar to you, maybe that's enough. If you need to go back and look in 12.4, that's, if I'm not mistaken, that's where you can find it. Yeah, pretty sure. Okay, so now let's do all of this. Let's do the special case of this. Of surface area. Where S is the graph of a function. Again, xi plus yj plus f of xy. Okay, so the special case of this integral here for the scenario where we have the graph of a function. So what is r sub x? R sub x is 1, 0, f sub x. We need r sub y, which is 0, 1, f sub y. And the integral is the integral of the magnitude of the cross product. That cross product is something that we computed last time. R sub x cross r sub y. Remember, that's just minus f sub x minus f sub y plus k. So then the magnitude of r sub x, and this is, from part 3 of the lecture, magnitude of r sub x cross r sub y is then just the square root of, and we don't need the minus signs anymore since those will go away, when we square magnitude of f sub x squared plus f sub y squared plus 1 squared, which is 1. So then the surface area is just, so in this case, surface area of S is the double integral of this. Where, I don't know, we could still call it D, I suppose. Whatever the D is now then a region, a rectangle in the XY plane, or maybe not a rectangle, but whatever the appropriate region is. Okay, so let's look at an example. Actually, let's work problem number 38 from the book. Here we're asked to find the area of the part of the plane 2x plus 5y plus z equals 10 that lies inside the cylinder x squared plus y squared equals 9. Let's get a bit of a grip on this. So what is this? This is a cylinder, circular cylinder centered along the z-axis, right? So so we've got a circular cylinder, and then the plane is going to cut through this cylinder at some angle. So, you know, if the plane is going like this, then there's a portion, right? Something like this. We want the area of the portion, that part of the plane that is inside the circular cylinder. Well, is this the special case? Do we have to do the general case, or do we have the special case? And the answer is we have the special case, because z for the surface that we're interested in, z is a function of x and y. Z is equal to 10 minus 2x minus 5y. So then what we need is the square root of f sub x squared plus f sub y squared, and we will then integrate over this region here. So this is a polar coordinate context, right? We're integrating over the circular disk to get this surface area. Okay, so then f sub x is minus 2, f sub y is minus 5. So then the square root that we're looking for is then the square root of -2 squared plus -5 squared plus 1, which is the square root of 4 plus 25 plus 1, so 30. All right, so we integrate 30 over this disk. So it's when we, I'm sorry, not 30, square root of 30. R dr d theta. And actually, let's just let's just do this as quickly. This is just the full circular disk. Radius equals, what was it, 3? So since this is the square root of 30 times the double integral dA, we remember that the double integral dA is just the area of the disk. So this is then the square root of 30 times, and then the area of that disk is pi times 3 squared. So 9 square root of 30 times pi is the answer there. This this little maneuver here where you know, I'm both lazy, I'm a little bit lazy, but I'm not so lazy that I don't actually draw it out and kind of, you know, write a little bit down. So it's good to be lazy. I want you to be lazy. I want you to think your way into some laziness, but I also want you to write something down so that it's clear the direction of your laziness. And of course, I say lazy, again, lazy is good, but we also want to be clear.